Let's look at some examples here of aromaticity. So we're going to start off and go through a couple of these things, and we'll make some notes on what those rules were. So let's take a look at example number 1 here. So this is a molecule, number 1, that we have to determine if it's cyclic and planar. It's definitely cyclic, and it's probably flat also. And number 2, do we have a conjugated pi system here? And remember, what we're looking for there is that atom. So that atom is sp3. So because of that, nope, we do not have a conjugated pi system. So that means that this compound is non-aromatic. All right, what about this next compound? So this next fellow over here is an ion. So let's go through the rules. So number 1, is it cyclic and planar? Yes. Number 2, do we have a conjugated pi system? Well, the question that we have to ask ourselves here really is what's happening right there. So really, the trend to note here is when you have a carbon with a negative or a positive charge, it's most likely going to be sp2 hybridized. I think without exception, this is going to work for us as we go through this chapter. So that carbon has a negative charge, therefore it is sp2. That means that it has a p orbital that's coming in and out of the plane of the page. So all of these atoms have p orbitals here. They're all lined up, so we have a conjugated pi system. All right, so what about 4n plus 2 electrons? Well, let's count them up. So we got 2, 4, and these electrons, and this is important, these electrons are in the p orbital. So they're counted. So 2, 4, and 6. So that gives us 6 electrons. That is a aromatic number of electrons. Think of benzene. So this is aromatic. All right, what about cyclooctatetraene? So let's take a look at this molecule here. So with this molecule, are we cyclic? Yes. Are we planar? Let's wait and talk about that in a second. Number 2, do we have a conjugated pi system? Well, let's wait on that guy for a second too, and let's look at number 3. Let's figure out how many electrons we would have here. So see if you can follow me on this. So if we were planar, we would have a conjugated pi system, and the number of electrons we'd have there is 2, 4, 6, 8. So then in theory that would be 8 electrons, which is a 4n number. So that number is an anti-aromatic number of electrons. Now this molecule doesn't care about Huckels' rules, it just wants to adopt its lowest energy conformation. So it turns out that with 8 carbons set up like this, that we can end up having this molecule adopt what we call the boat conformation. So it actually starts to bend down and does something like this. Now, what's the purpose of that? So as it's sitting flat like this, all those p orbitals are lined up and we are conjugated. As we bend up though, those p orbitals here come in and out, and these are up and down. So they're not aligned anymore. So then we do not have a conjugated pi system, and we are also not planar because we're bent up like that. So if a molecule is long enough, really large enough, I guess is the better word, to adopt a bent position, or if it's flexible enough to avoid being anti-aromatic, then it typically will. So down here it says larger annulenes with 4N systems. Well, they don't usually show anti-aromaticity because they have the flexibility to adopt non-planar conformations. So that's kind of just one you have to commit to your memory, that this thing's big enough that it can bend. So typically if a molecule can avoid being anti-aromatic, then it'll try to do that. All right, what about 10-annuline? In 10-annuline, I want to point out in this conformation that we're all cis, so everything is cis here. Now, one of the problems that you have is that when you build a molecule like this and you start getting it larger and larger and larger, with those double bonds going from benzene to cyclooctatetraene up to this 10-annuline, you get some strain right here, because this really wants to be 120 degrees because it's sp2, but it starts getting bent and stretched out, right? There's this pressure stretching it out right here that causes it to start to bend. So this molecule actually is also not planar, and because it's not planar, it is non-aromatic. Right, so that's if we're all cis. Now if we're trans, and this is one that pops up in here too, it has 2 trans positions in it. So electron-wise, 2, 4, 6, 8, 10, that is an aromatic number of electrons. But this H atom and this H atom are pushed in towards each other. So as a side angle, what you can kind of see here is one H comes up, and then the other H here is down like that. And that causes, that steric interaction causes this to twist so that we're not conjugated anymore. So this is also non-aromatic. So again, that's another one that you kind of have to commit to memory. Now, what about these guys down here? So there's a little summary that I wanted to point out to you. So 10, 14, 18, etc. annulenes. So these are all aromatic number of electrons. They can, if you get big enough, if the number of carbons gets large enough, especially if we have a mixture of cis and trans, right? So if you look at the molecules down below, we have a mixture of cis and trans. We become large enough to adopt planarity, and then we become aromatic. So big molecules like this with cis and trans mixed in, we can adopt a flat structure. Right? When we get up to the 10-annuline with all cis, it's just not flexible enough. All right, let's look at a couple more examples down here below. So let's talk about heteroatoms. So heteroatoms are atoms like oxygen and nitrogen and boron and sulfur. So these, when we talk about aromaticity, these kind of can make a decision whether or not to be sp2 or sp3 hybridized. It's really based on resonance and whether or not that resonance leads to an aromatic situation, because that would be the lowest energy. If it leads to anti-aromatic, then it would be higher in energy. So let's look at this first problem here. So number 1, are we cyclic and planar? Probably, right? Definitely cyclic. This is probably going to be flat. What about a conjugated pi system? Well, let's talk about this. So we've got sp2, sp2, sp2. So this atom is sp2. Now, by the way, these electrons right here are in an sp2 orbital also. Okay, so conjugated. Well, what about this oxygen? So I hope that you all remember that this structure has resonance. You have a set of electrons adjacent to a pi bond, so we have resonance here. So with that resonance, we're going to end up having a double bond there. So that means that one set of these electrons has to be in a p orbital, and that leaves us sp2. So this is a conjugated pi system. So what about the number of electrons? We have 2, 4, 6 electrons. That's an aromatic number of electrons. Well, what about this next molecule? So looking at this molecule, well, we can say right off the bat, this is kind of a problem here. So that is sp3. So with sp3, that means that this is non-aromatic. Okay, we don't have to worry about counting electrons or anything like that because it's not a conjugated pi system. Right? What about this next guy? Well, let's take a look at it. So that carbon right there has a plus charge on it. And we said when that situation arises that we assign hybridization of sp2 to that carbon, which means that we have an empty p orbital pointing in and out of the plane of the page right here. All right, so that's empty. There's a p orbital here, and here, and here, and here. All right, so we are cyclic. We're planar. So are we conjugated? Do we have a conjugated pi system? Well, if we make this sp2, then this would be in a p orbital. Right? That makes sense too because remember, we have resonance here. And in order to have resonance, we have to have overlap of p orbitals to make a pi bond. Right? So resonance structure of that, we could go either direction, but this would be one of our resonance structures. Among others, there are others that are here. So then that would give us a negative charge here with a positive charge there. That's going to be a pi bond. And then this situation. Okay. And again, there's others that are here, so we'll just write etc. there. So anyway, conjugated. A p orbital here, a p orbital, a p orbital. That's in a p orbital, and a p, and a p. So we are planar and conjugated. How about the number of electrons? Well, you got 2, right? 4, 6, and then none right there, but that's 6. So 6 electrons. That is an aromatic number. This compound is therefore aromatic. All right, let's look at the next 3 down here below. Well, this one's interesting too. So let's take a look at it right off the bat. So do we have a p orbital everywhere in the structure? We have the potential. So there's an sp2 here. That's sp2. This is sp2, sp2, sp2. And we could make this sp2. And because remember, like that last problem, we have resonance here. So that means that we can have a p orbital there also, right? Now, we have p orbitals everywhere right now. But in the structure right now, this p orbital here is kind of talking to the p orbital that's over here. So it's not part of the aromatic system right now. But watch this. What we can do is we could take these electrons and pull them over like this, swing these over here, and then kick that up just like so. So when we do that, we're going to end up with our oxygen here and a minus charge, double bond, double bond, double bond. And now we have something that looks like a weird Frankenstein version of benzene. So here you have a conjugated pi system, you're cyclic, you're planar, and you have 2, 4, 6 electrons. That is aromatic also. All right, so what about this next guy over here? Well, this one's interesting. So cyclic and planar. Let's go through these. So cyclic, yes. Planar, maybe. What about a conjugated pi system? Let's come back to this guy. And let's take a look here. This is another if. So if we assume that that was flat, if we assume that it is a conjugated pi system, then we would have 2, 4, 6, 8 electrons. That's a 4n number, and that's anti-aromatic. So if we make this oxygen sp2, then we get anti-aromatic. So the molecule doesn't care what we assign it, right? It's just going to adopt its lowest energy conformation. So it's not going to decide to make this choice, really. It doesn't have a choice. It's just going to be the lowest energy. So instead, it actually is going to be sp3. And that means that we don't have a conjugated pi system. And because of that, this molecule is non-aromatic. Now that only works with these heteroatoms. If that was a carbon with a minus charge on it, then you'd be stuck with 8 electrons, and it would be anti-aromatic. Okay, so let's take a look at this last one here, and let me zoom in a little bit. So what about this guy? So let's figure out what our hybridization is on each of these atoms. So we're sp2, sp2, sp2. This is sp2. That atom is sp2. And this we have to decide. So it can make it a choice, essentially, right? We have to figure out what we're going to do. If we decide that that's sp2 and it leads to aromaticity, we made a good choice. If we decide it's sp2 and it leads to anti-aromaticity, then we were wrong. So let's take a look at it. Let's assume that it is sp2. If that's the case, then we have resonance that would do this. So then our resonance structure of that would look like this, with our double bonds here staying in position, double bond here, H, and then an O with a minus charge and a plus charge right there. So now if we look at this resonance structure, we're cyclic, we're planar. Do we have a conjugated pi system? Sure, we do. How about the number of electrons? 2, 4, 6. So we've got 6 electrons here, and that means that we are aromatic here. Now, other thing to point out, and this is a question that comes up from time to time, and it's an important biochem question too, is let's look at these nitrogens. So we have one that I circled there that is red, and I'm going to circle this guy here. So the question is, which one of these nitrogens are basic? So basic means that we can grab an H. So this set of electrons right here is not readily available to make a bond with an H atom. Right? Instead, it's involved over here, right, in this pi bond, where this set of electrons here is in an sp2 orbital, and it is more basic. That idea of basicity can be further explained by looking at these two molecules. So let's put our double bonds in just like so. Let's look at that molecule versus this 5-membered ring version of that same kind of situation where we got a lone pair adjacent to these pi bonds. All right, so the question is, which one of these is more basic? So basic means that we're grabbing an H, right, from like H3O plus or something like that, right? So we're grabbing an H from there. So if we grab an H, it's going to go to nitrogen, and it would give us this, right, with a plus charge there. And then our double bonds, of course, stay here. And then the same idea up here above. If we add H3O plus here, you're grabbing an H from that H3O plus. So then our structure is going to be this guy. Well, let's take a look. This is a question, a thought question that comes up sometimes. So let's look at that molecule up on the top. Is it aromatic? Here. So let's look at this. So let's take a look. We are cyclic and planar. We have a conjugated system, and we have 6 electrons. So this is aromatic. Well, nothing's changed except this positive charge over here. So we still are cyclic, we still have a conjugated pi system, and we have 6 electrons still, so we're still aromatic. What about this guy down below? So, number 1, are we cyclic and planar? We are. Number 2, do we have a conjugated, right, pi system? Well, if we make that atom sp2, which it is, then these electrons are in a p orbital. So then we are conjugated. And how many electrons do we have? 2, 4, 6. 6 electrons. That means that we are aromatic here. Oh, what about this guy? Well, right off the bat, that cannot be sp2. That is sp3, which means that we're non-aromatic. So this molecule with that nitrogen that's protonated actually is a pretty strong acid. So the nitrogen that's involved in resonance in the structure down below is not basic. So remember that these electrons, and this is important too, those electrons are in an sp2 orbital. They're not involved in resonance at all. So they're just ready and able to grab a hold of a proton.